Hello, everyone. We're back again. Time for some fun. Do some cool capacitance problems and hopefully finish up a chapter on capacitance. Anybody have any questions while we're waiting for everybody else to come in? I'm going to post a test. So we did the test on chapters 21 and 22. We should be finished today, of course, with chapter 24. So I'll post the test either today or tomorrow, but I'll give you until Wednesday to get it done. That way it's aligned with your homework due date as well. But I would probably use this weekend to get one attempt out just in case you forget, so you don't get a 0 on a test. Remember, that's an online test. You get taken a bunch of times. I think I let you 3 times on this one, and only your highest score counts. So I would say take the practice test several times. That should help you also with a little bit with the homework, because you're going to see a lot more problems when you're taking the practice test, and some of those are a lot easier than the ones that you do in the homework. So sometimes it'll help you with the homework as well. So I prefer that students basically do as many problems as possible. So I would, normally just tell students to do all the odd problems at the end of each chapter, because those have the answers in the back of the book. The closest you can come to that is doing the practice test repeatedly and really doing the homework. So, ideally, I'd like to tell you, do all your homework first and then try to practice this. No. That's good, but sometimes the homework is a little more difficult than you can get without more practice. So if you find that's a problem, then go back and start taking some of the practice tests, and maybe I'll help. So looks like everybody, we got 13 people in here. Looks like no one has any questions, so I guess I'll go ahead and get started. So we're still talking about capacitance, which remember we defined as charge per unit voltage. So C equals Q over V. Last time I spent my time mostly teaching you about how to apply first Gauss's law to calculate the electric field, then V equals the negative integral of E dot dl to calculate the voltage between 2 parts of a capacitor, and then using C equals Q over V to calculate the capacitance itself. Then I ended up showing you the 2 equations necessary to find the equivalent of 2 capacitors in series, and that was a weird formula: 1 over C equivalent equals 1 over C1 plus 1 over C2 plus 1 over C3 ... And then I did it for in parallel, and those ones actually came out pretty easy, which was C equivalent is equal to C1 plus C plus C3 ... So I'm going to recap that. Of course, you'll see it in the equation that I'm writing, but I'm getting ready to do an example to show you how to break down such a circuit. So let's get started on that. I want to open up my document cam, and here we go. So those are the equations we learned last time. I know they're not crystal clear. There you go. This is the one for series. Notice I put the S here. This is the one for parallel, so I put 2 parallel sides. So when capacitors are in series, their reciprocals add to give the reciprocal of the equivalent capacitance. When they're in parallel, their actual hold on, guys, coming in. When they're in parallel, their capacitances add to give you the total capacitance. Okay, so I'm going to show you how to attack a circuit like this. Normally, when I take a circuit like this, notice this is a voltage or a battery here. I'm just trying to find basically a circuit where I can set up this battery, which say, let's say V equals, I don't know, 50 volts. Okay. And what I want to be able to do is create a circuit that has this battery and 1 capacitor, period, and the battery wouldn't know any better. In other words, the battery still thinks a certain amount of charge left, and that's it. So let me show you how to do that. I'm going to first attack C1 and C3, or excuse me, C2 and C3, which, by the way, I have the numbers over here. Notice their subscripts are equal to their capacitance in microfarads. So the innermost ones, in some sense, are the C2 and C3. So I'm going to immediately write, here's my battery. Come out here, here's C1. And I'm going to replace C2 and C3 with just a new capacitor, C. And what that's going to be is C equivalent to 3. is going to be equal to, notice they're in series, so I got to say 1 over that is equal to 1 over C2 plus 1 over C3. Well, that's 1 over 2 plus 1 over 3 microfarads, which of course is equal to 3 plus 2 over 6. So you end up getting 5 over 6 R C equivalent is equal to 6 over 5 microfarads. So that's 1.2. So I'm going to put this up here as 1.2 microfarads. Everybody see how I did that? I just fixed that one now. The rest of the stuff is still the same. I now have a, in this case, this guy is still going to be a 4 microfarad. And then this is going to go off into 2 with a C5 and C6. I'm leaving it like that. Now, this one was actually equivalent to that one, so that's what I'm trying to show is a stream of equivalent ones. Now, in this case, I have 2 that are in parallel, and of course, they're the easy ones. So I'm going to say 1.2 plus 4 is 5.2. So I'm going to say, now I have 1 microfarad right here in series with 5.2 microfarads for this guy. And then notice this one, C5 and C6, that's 5 microfarads and 6 microfarads. So that should give me 11 microfarads. Again, because they're in parallel, they add the easy way. So this is C1, this is the equivalent of those 2, and this is the equivalent of those 2. And now I can draw my battery right here. Now I have 3 in series, so I got to do that weird thing. I'm going to say 1 over C equivalent. Now this is the actual C equivalent we're trying to look for, right? This will be the total answer. So 1 over C equivalent is going to be 1 over 1 plus 1 over 5.2 plus 1 over 11, which might be better if I say 1 over 1 plus 10 over 52 plus 1 over 11. Okay, then I can just get a common denominator, and obviously the least common denominator between 52, 11, and 1 is 52 times 11. That's not actually the simplest, but it's the one I'm going to use because it's easier to figure it out. I could try 104, but the outer digits don't add up to be the inner digits, so I know that's not it. I could try 156. 1 and 6 does not add to give me the 5, so that's not it. So I'm just going to do 11 times 52. 10 times 52 is 520, so this would be 572. So I'm going to say 572 over 572 plus 11 times 10 is 110 over 572 plus 52 times 11 or 52 times 1 is what gives me this. So 52 over 572. So now I can see that 1 over C equivalent is really what? We got another person coming in. Is really 572 plus 52 would be 624, 724, 734. So 734 over 572. That means C equivalent is equal to 572 over 734. Now here's where I'm going to try and make sure that that's right. 572 divided by 734. That gives me 0.779 microfarads. Now I'm going to try with these original fractions just to make sure that this is right. So I'm going to say 1 plus 1 divided by 5.2 plus 1 divided by 11 And now I'll do 1 over that. Yep, I got 0.779, 10 to the negative 30. Yeah, so that's it. So that is the equivalent resistance. So what that means is I can write this with 50 volts opposite a single capacitor that has a 0.779 microfarad capacitance. So this circuit is exactly equivalent to that one. Now, the other part I can do with this now is I can say, okay, well, I know how much voltage is going to leave here, or excuse me, how much charge is going to leave here, because I know that C equals Q over V. So I'll call this the extra part. So C equals Q over V tells me that Q is going to be equal to C times V. So I'm going to take that C, which is 0.779 microfarads. Notice how I'm keeping the microfarad there. That'll tell you something in a second. 0.779 microfarads times 50 volts. Well, volts, not microvolts. Okay, when I multiply these two, I get 38.96. Now, a volt times a farad turns out into a coulomb, but I had a micro there, so this is 38.96 microcoulombs, and I carried 1 extra digit. So that's how many charges left. Now, what that tells you is that 38.96, which you roughly call 39.0 coulombs, is going to go out and highlight or basically charge this side at positive 38.96. This side is going to be negative 38.96. And then what's going to happen is that 38.96 that was here, because this is negative, that's going to be forced over here, but it's got 2 choices. It's got a choice of doing some of it here and then doing some of it here. Well, at that point, what you have to do is say, well, these two are in parallel, so the voltages have to be the same. So you'd say V23 is equal to V4, meaning the voltage across capacitance C2 and C3 is the same as the voltage across the capacitance C4. And you could use that to find the charges. And then, of course, that one charge that goes to this 1.2, that's going to be spread evenly, being the exact same thing, that is, on C2 and C3. And the charge that you get using C4, that's going to be on this one. And then again, coming out of that, it's going to be still that 38.96. And now part of that's going to go to C5, part of that's going to go to C6. But that's, in fact, exactly caused by the voltages being equal. So let's sort of work through that. So first off, I can see that Q1 is going to be 38.96. Whoa, I wrote that backwards. I got dyslexic all of a sudden. So that's 38.96 microfarads. That's what's going to be on that charger, on that capacitor right there. Okay. Now, what happens then is that 38.9 is going to go to here and here. Is going to go there, but some part of it's got to go to here, which is 4 microfarads. And the other part, of course, is going to go to here, which is 1.2 microfarads. Okay, well, they're in parallel, which in our labs later we'll learn that parallel means the voltage across the 1.2 is equal to the voltage across the 4. So whenever things are in parallel, their voltages are equivalent. We know that C equals Q over V. So what we have here is that Q 1.2 plus Q4 has got to equal 38.96 microfarads. That's just conservation of charge. I got 38.96 Q1.2 is going to go to this top leg, and Q4 is going to go to this bottom leg. So that's one equation. The other equation I have is that V1 is equal to V, or V1.2 is equal to V4. And of course, that means that we're going to have, if you solve this for V, you can see that's Q over C. So that's Q over 1.2, or Q 1.2 over C 1.2 equals Q 4 over C4. Well, that's pretty straightforward. What that means is Q, I just changed symbols for some reason, sorry, Q 1.2 over 1.2 microfarads is equal to Q4 over 4 microfarads. So I'll come back here, and what that means is I'll do Q4 is equal to 4 microfarads divided by 1.2 microfarads times Q 1.2. This was actually 6/5 if you want to. That doesn't really jump out at me as anything easy to switch to a fraction. So I'm just going to do 4 divided by 1.2. And I get 3.33. And I'm assuming these 4s, when I give these one digits like this, like these things over here, I'm pretending they're all 3 sig figs, even though I didn't write them that way. Apologize for that, but that's why I got this, and that's times Q 1.2. So now I have an expression for Q4 in terms of Q12, so I can put it back in that equation. So now I'm going to say Q 1.2 plus 3.333 Q 1.2 is equal to 38.96, carrying that extra digit. I should have underlined it up there as well. So I think you can now see that Q12 is going to be equal to, basically I got 4.333 times Q12. So I'm going to divide both sides by 4.333. And that gives me 8.993. Okay, and notice that was microfarads. I don't know why I wrote farads there, but that was microfarads. So when I divide it by just a pure number, 4.333, I get microfarads again. So this is microfarads. So now we have the charge on the 1.2 leg. Notice that was a combination of the two. What that means, though, is that since these two are going to have basically the same amount of voltage across it, you can then say, okay, well, V2 plus V3 has to equal the total voltage, which is the same as we got over here. We can now figure out what that total voltage is, V1.2, from this. I'm just going to take Q4 and divide it by C4. Well, Q4 we found, we didn't find yet, but I'm going to in a second. That's going to be 3.333 times Q12, which we found was 8.993 microfarads. So what I'm using is this expression right here to find that voltage. Now I got to divide that by 4 microfarads. Again, I'm pretending like that's 3 sig figs. So I do 3.333 times 8.993. And then I'm dividing that by, oh, this is microcoulombs, by the way, not microfarads. Now I'm dividing that by 4. So I got 29.97. So V 1.2 we know is that divided by 4. So that's 7.493. And that is actually, since the micros cancel out top and bottom there, you can see that it's just going to be coulombs per farad, which is a volt. So 7.493 volts. So now, because I know the voltage across here, I know the voltage across here, and I know that V2 plus V3, the voltage across capacitor 2 plus the voltage across capacitor 3, has to add to give me that 7.493. So now I can, I already have some values here. I have Q12. That's actually not valuable because that's not one of the original things, but this is Q4. So that is valuable. So there's one answer. I also got Q1, which was the charge on capacitor 1. I've got the charge that went to 1.2, but that doesn't help me because 1.2 is made up. So now what I'm going to do is realize that C equals Q over V, and that C1, let's see, I want V to be the same, so I'm solving for V. V would equal Q over, so Q1, or Q2, I should say, Q2 over C2 plus Q3 over C3 has got to equal 7.493 volts. Basically, this one's going to climb you up, or excuse me, if I go this way, I'm going to climb up a hill a certain height. And then when I get to here, I'm going to climb up another hill a different height, and then I'll be at the exact same height as this side. Well, this side started at 0. You can pretend it started at 0 and only went up by 7.493 volts. That's how high it went up. So these two have to add up to give you 7.493 volts. That's what I'm doing there. Okay. I know C2 and C3. Now I just have to solve for Q2 and Q3, but I also know that Q2 plus Q3, actually, I know that Q2 and Q3 actually have to be equivalent. Because what's going to happen is whatever charge is this one, that positive charge is going to make the negative charge the same over here. That's going to push it off that way. Does that make sense to you guys? When I put a charge, say 4 microcoulombs there, this is going to make this negative 4 microcoulombs. This was isolated before, so now this is going to become positive 4 microcoulombs, so on and so forth. So in fact, it looks like both of them are going to get the same charge. So what I'm going to do is make sure that I'm right by this. And the way I'm going to do it is I'm going to say both of those Q2 equals Q3 equals 1, or excuse me, what was the Q12? Equals 8 point, no, it can't be the same as that. It has to be what's left over, excuse me. So it equals, remember we said a certain amount of charge is going to go to the top leg and a certain amount of charge going to the bottom leg. The sum of those two had to be 38.96. I just figured out what went to Q12. So now I have to say, well, what's going to, that's what that was. Now what's going to Q4, which was the one by itself, right? Yes. Okay. So Q2 plus Q2 and Q3, I already had Q4, right? Yeah, I did have Q4. So that's what went to Q4. The other part of it, which goes to Q1 and 2, is going to be the 38.96 microcoulombs minus the 29.97 that went to the Q4. Now, I think you'll see what this is going to be. It's going to look just like that, basically. So when I do that, I do 38.96 minus 29.97. And that gives me 8.99 microcoulombs. And in fact, earlier we had called that 8.993. So I'll carry that 3 microcoulombs. That should be the charge on Q2, and that should be the charge, or excuse me, that should be the charge on capacitor 2, and that should be the charge on capacitor 3. If I did this right, then the voltage across that plus the voltage across that should add to give me the same voltage for 7.493. So let's just double check that. I'm going to put this as if it's the answer, but I'm going to check it just to make sure. So when you're doing these, you can get lost really quickly, but you just keep plugging on and then check to make sure they work as you go along. So V2, which is actually C2 over Q2, excuse me, Q2 over C2. Notice the V comes up here and then the Q stays up top. So it's actually Q2 over C2. That should be 8.993 microcoulombs divided by 2 microfarads. So that should be around 4.5. So 8.993 divided by 2 gives me 4.497 volts. And now V4, or excuse me, V3, which should be Q3 over C3. Well, that should be, again, the same 8.993 microcoulombs divided by, in this case, 3 microfarads. And that gives me 2.998 volts. So if I add these two numbers, they should give me that 7.493, and then I'll know they're right. So V2 plus V3 is equal to 4.497 volts plus 2.998 volts. And I get 7.494, which is close enough. So now I have figured out the charge on charge 1 on capacitor 1, on capacitor 2, on capacitor 3, and capacitor 4 now. All that's left now is, remember, we had the same thing going on here. 38.89 or 38.96 coulombs is going to come across here, and a certain fraction of that's going to here and a certain fraction of that's going to here. Well, because they're in parallel, what dictates that is the two voltages have to be equal. So now I have Q5 and Q6. So Q5 plus Q6 have to add to give me 38.96 microfarads. One extra sig fig, don't forget. But I also have that since the voltages have to be equal and voltage is equal to charge per capacitance, then I have Q5 over 5 microfarads plus, or is equal to Q6 over 6 microfarads. So from this one, I can say that Q6 is going to equal 6 over 5 times Q5, which is pretty nice because that's just, again, 1.2 times Q5. Now I can plug that back into here, and I'm going to say that Q5 plus 1.2 times Q5 is equal to 38.96 microfarads. That means Q5 should be equal to basically 2.2 divided into 38.96. So I do 38.96 divided by 2.2. and that gives me 17.71 microfarads for Q5. So I have another answer. Notice I'm trying to, even though I'm sort of at random using different colors for the calculations, I don't know why I'm doing that, but I am. But I'm trying to at least identify the answers by boxing them off with a different color. And now, of course, Q6 is just 1.2 times that. So I'll say times 1.2, and that gives me 21.25 micro. Oh, that was supposed to be microcoulombs, by the way, not microfarads. Stupid head. In fact, that was too. I don't know why I wrote farads everywhere. Let me fix that real quick, everybody. See, I had it. Let's make sure I had it right up there. Nope, I had it wrong there too. What the crap was I thinking? So I fixed that one. This one's a Q. This one's a Q. So now I can put this coulombs here. That'll make that right. And I can box off this. Now I have all the charges. And in fact, if you remember, the way voltage works is like climbing a mountain. And basically, when you start here, you go from here to the top of the mountain, which is, this is like ground level. Okay. The low side of the battery you can treat as ground. And then you go up to 50 volts. Whatever the voltage across this was, you're going to step down that much. So let's check and see all this stuff works. So V1, which is equal to Q1 over C1, that's actually going to be, we found Q1 was 38.96 microfarads, again with one extra. Dang it, there I go writing farads again instead of coulombs. Urgh. I don't know whose fault it is. I'm going to assume it's one of you guys. Over 1 microfarad, which is easy peasy. That's 38.96 volts. Okay, so what that means is if I drew a little bubble right here, this would read 50.0 volts. I know I sort of in the glare there. And then a bubble right here would say, well, I just dropped down 38.96. So 50 minus 38.96. Might help if I hit the decimal places instead of zeros. That gives me 11.04 volts. So this bubble up here is now 11.04 volts. Okay. Now, when I go across this, this should be, remember we calculated that the voltage across Q12 was 7.493. So right here, this bubble should read 11.04 minus the 7.493. So 11.04 minus 7.493 gives me 3.547. Which, by the way, 11.04 only had one pass a decimal place. So this one really has only one pass a decimal place. So that should be just 3.55 volts, basically. So that's what the voltage is there. Now, this is supposed to be 0 volts, and this is supposed to be 50 volts, which obviously it is. So when I subtract whatever voltage is across C5 and C6, they're the same voltage. That better give me 0 here, right? Because I'm at 3.547. There's no way to drop from here to here or from here to here. So this is 3.547. This is 3.547. So let's check the voltage across C5. The voltage across C5, so that would be V5 is equal to Q5 over C5. Notice I've just haphazardly throwing in big Q's and little Q's. I have no idea why I'm doing that, but they're supposed to be the same thing. So I'm going to take that 17.71 switch to black now just to keep things interesting. 17.71 microcoulombs divided by 5 microfarads because it's C5. So 17.71 divided by 5 gives me 3.542. Yay, we're right. 3.542. And this one really should be 3 sig figs, so I only got that, and that should be volts. So you can see that, in fact, this was 3.54 to 2 decimal places, which is really supposed to be accurate only to 1. This is 3.542, which is only supposed to be accurate to 2 decimal places. They even match really within rounding errors at the 2nd decimal place, but you can see that now the voltage is in fact 0 volts there, because that's how much it's got to go down from here to here is the same as the voltage that has. So now we've corrected it. Now we can tell at any point in this circuit what the voltage is, what the charge is, and that's sort of the nastiest scenario you could sort of come up with a series of capacitors is add them all up, find out what their, find out all their equivalent capacitances, then find out all the voltage at each spot in it. But that's how I did it. Just to recap what I did, because I know it was a lot. I realized I had a 50 volt source here, and I had 1 microfarad, 2 microfarads, 3 microfarads, 4 microfarads, 5 microfarads, and 6 microfarad capacitors. That's why I labeled them that way. And I one by one started from the deepest one, the one sort of, I just say innermost, like this. So those two are in parallel. I mean, in series add like funky stuff. So I took the 1/2 microfarads plus the 1/3 microfarads and said that's equivalent to 1/C equivalent. So then I just used a common denominator and found that was 5 6. So the C equivalent was 6/5 microfarads, which 6/5 is the same thing as 5 1/5. So that's how I knew it was, or excuse me, is 1 1/5. So that's why I knew it was 1.2. So I then replaced that guy with a 1.2 microfarad capacitor. That's what I see here. Now I have 2 in parallel, a 1.2 and a 4, and I have 2 others in parallel, a 5 and a 6. So all you have to do when they're in parallel is you just add them. So 4 plus 1.2 gave me 5.2, and 5 plus 6 gave me 11. So that's where that came out. Okay, now I had 3 in parallel, and I did some really crazy math, but basically it's all arithmetic. You can just throw it in your calculator. That's all you need to do. And what I found is all 3 of these together could be replaced by a single 0.779 microfarad capacitor. That's what that is. So this whole bank of capacitors could be erased if you could just buy a single 0.779 microfarad capacitor. So then using that, I can say, okay, well, that's really easy because now I have a single capacitor connected to a single battery. I can use that to figure out how much charge is going to be dispersed by, or, sent out by the battery. So doing that, I just said, okay, let's take, for instance, this is where I came down here. Let's take, for instance, the voltage that the battery had, and using C equals Q over V, the voltage the voltage multiplied by the capacitance would actually give me the charge that left. And I'm looking for where I did that now. I would have thought I did it right by that, but I didn't see it there. Nope, that's not it. Nope, that's not it. No, that's not it. 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 Oh, here. Nope, that's not it. Where did I do it? C equivalent. I should find a 0.779 somewhere times a 50. 0.779 times a 50. I know I wrote it somewhere. Should be 38 something other. Here it is. Okay. So here's where I went back and said, all right, that's why I saw this 1.2 and I thought that was a subscript on the C. It's just referring to this capacitor. That's what it was. So now I take and analyzing basically just this final part of the circuit, which is that. I multiplied 0.779 microfarads times 50 volts and got 38.96 microcoulombs. So that's how much charge will be leaving the positive side of the battery in terms of conventional current. So now I take that and say, okay, well, 38.96 coulombs goes from here. That's obviously going to be stopped right here. So this left side is going to be charged at 38.96 microcoulombs. The right side is going to basically be compelled to lose 38.96 positive coulombs or positive microcoulombs of charge and push it along this way. So this one will be negative 38.96. That means 38.96 positive charges are going up this wire, and some fraction are going to go to C4, and the other fraction is going to go to the equivalent 1.2, which is really just 2 and 3. At that point, I then had to say, well, they're going to be in parallel, so their voltages had to be the same. So what I did was set the voltage across 4 equal to the voltage across 1.2, which you can see I did right here. Again, voltage is Q over C. So I had Q going to the 1.2 microfarad over the C12, which would just be 1.2 microfarads, is equal to Q4 over the 4 microfarads. So that gave me an ability to solve for Q12 in terms of Q4 or for Q4 in terms of Q12. I chose the latter. So Q4 became 4 over 1.2 times Q12, which is 3.33. But I also knew that charge had to be conserved. So if 38.96 coulombs goes there, whatever part goes here plus whatever part goes here has to add up to 38.96. So that's where I got the other equation, which was Q1 plus or Q1.2 plus Q4 has to equal 38.96. So then when I just plug this into that, I got this. Notice that's the 3.333 times Q12. That allowed me to solve for Q12, which was 8.993 microfarads. And then, of course, I can use that original equation, or I can use the expression. I could use this, for instance, and just do subtraction to get that number of microcoulombs. But I could also use what I found earlier, which was this equation or this equation. Q4 is equal to 3.333 times Q12. That's ultimately, you can see what I did. I did the 3.333 times 8.99 over to 4. That gave me the voltage across that bank again. And it also allowed me, of course, to determine what Q4 was, which is a 29.97 by multiplying 3.333 times the 8.993. Does that make sense to that part? So that was allowing me to find out how much charge went this way, how much charge went that way. My argument was that whatever charge goes this way, both of these two are going to do the same. So if it came up 4 microcoulombs on the left, and this is going to be 4 negative microcoulombs, this will be 4 positive microcoulombs, this will be 4 negative microcoulombs. And I confirmed that by taking the time to compute the actual voltage across V2 and V3, just to make sure that it gave me the same. And sure enough, it did. Right here, it gave me 7.493. So that was, and actually it was 7.494. I had 7.493. So that was plenty close enough. So that confirmed that I was telling you correctly that the two charges here are going to be identical. Then that same 38.96 is going to have to be distributed like it was before on these two legs, but this one's a lot easier because it's one capacitor on each side. You just have to set the voltages equal to each other, and the sum of the charges, Q5 plus Q6 equal to 38.96. I did that, and ultimately we were able to get all these different values, which showed all the different charges So I got Q5, I got Q6, there's Q5, there's Q6. I was even able to go back and figure out the voltage across 5, which is the same as the voltage across 6. And I saw that that was exactly how high above 0 volts we are when we got to that bubble right there. So just going through in a methodical way and calculating everything you can, remembering that one, voltages add across things in series, and two, voltages are equal on things in parallel. So the voltage across here is exactly the same as the voltage across here, whereas the voltage across this plus the voltage across this is equal to the voltage across the whole thing. Keeping all that in mind, and C equals Q over V, you can figure out all of it. So I'd originally just planned on showing you the capacitance equivalent, but at the end I decided I'm gonna go ahead and do this extra part, which is compute all those voltages, because I notice students have a hard time putting that together. But in principle, you'll see your book doesn't take time to do any of that stuff. It does sort of one problem to show you what happens to all the voltages, and it's not enough. So I thought I'd give you a little bit more. So I know that's a little confusing. You can go back, watch the video. I'm putting the videos up now, by the way. I'm putting them straight onto YouTube because I've decided that when I record them here, there's no bandwidth issues and you get a better image. So this document will be up shortly after class, and the video will be up usually about an hour after class. It takes about an hour to process and to upload. So that'll be up there as well on YouTube, and I'll put a link to it. But you can also go to my YouTube. I think I fixed my YouTube links. All of them had www instead of www to get to my YouTube channel. I think I fixed those now, so you should be able to get to that. All right, so let's look at another example. This is another example, sort of like one in your book. What I'm going to do is I'm going to take and connect a battery. Let's say a 36.0 volt battery, and I'm going to connect that to a capacitor. And now I'm going to say that capacitor has a capacitance of 4 microfarads, and I mean that is 4.00. Okay, write it like $1 there. And then this one over here is going to be 8.00 microfarads. And I'm going to do something kind of crazy. I'm going to charge these babies up. And then disconnect them, reverse them, and reconnect them. Okay. What I want to know is, in the end, what will be, and I'm going to call this C1 and I'll call this C2. What will be Q1 final, Q2 final, as well as Q1 initial and Q2 initial. So I'm using the big Qs to represent what happens right now just from connecting to the battery, and I'm using the little Qs to represent what happens to them after I've disconnected the battery, and then I disconnect these and flip them around and put them back together. Does that make sense? So I'm basically going to take the positive side of this and connect it to the negative side of that, and the negative side of this and connect it to the positive side of that, and the charges are going to rejigger themselves, and then you're going to try to figure out, well, what's the new one? So let's first off start with finding Q1 and Q2. So that's the first part. Well, what I know is that they're in parallel, so the two voltages have to equal, and in fact the voltages are 36 volts. If I put a little bubble there, What that means is I've got my voltmeter with the black terminal in the ground, or in the little mouth hole of the light receptacle. If you wanted to, that would be acceptable as well. And I put my little red probe from the voltmeter right here, and that's going to read 36. If I put it right here, it's going to read 0. And if I go along here, this wire has essentially 0 resistance compared to the other things in the circuit. So if I put it here, I'm going to get 36 volts as well. And here I'm going to get 36 volts as well. Again, no resistance from here to here. So this should be 0 volts. And this should be 0 volts. That's why in parallel, they have the same voltage. So I'm going to say V1 equals V2 equals just V, which is 36.0 volts. But remember, C equals Q over V. So that means Q1 over C1 is equal to Q2 over C2. Okay. So I know C1 and I know C2, but I don't know Q1 or Q2. So I have two variables there. But what I do know is I can replace this capacitor with an equivalent one. Anybody know what that equivalent capacitance would be? I've got a 4 microfarad and an 8 microfarad, and they're in parallel. Here's the formula we're looking at. I think I heard somebody say it correctly. Here's the formulas we're using, these two purple guys. So which one are we going to use? The one on the right or the one on the left? In the purple at top of this page. Everybody see we're going to use that. And that makes it easy because this one's just going to be 12.0 microfarads. So the other thing we know is that V is equal to Q1 over C equivalent. Okay. And in fact, well, we'll do basically that. It's just going to be equal to Q. I'll leave that 1 off and let you figure out that in a second. So it's the charge that's going to come out there is C equivalent times this. So I'm going to find out what that charge is. That charge Q is going to be C equivalent times the voltage. Well, the C equivalent is 12.0 microfarads. And the voltage is 36.0 volts. So 36 times 12 is like super easy, right? Nope, it's not. Well, 36 times 10 is 360. 36 times 2 is 72. So I'm going to say that's 432. And that's microcoulombs. So that's the total charge that leaves the battery. And then, like we learned before, when a charge leaves the battery, it has to decide how much is going over here and how much is going over here. That's not unlike current leaving a battery going into resistors, only resistors behave differently than capacitors. Like most of the current will go through the biggest resistance. In this case, most of the charge will go in the smallest capacitor. So we can now work that out. I know that Q1 plus Q2, I was going to write that over here, but I chose not to. That's why I started with a 1. Q1 plus Q2 is actually equal to Q. So now I have two equations and two unknowns. I have this equation and this equation. So I'm going to call this equation 1. I'll call this equation 2. So 1 is going to imply that Q2 is equal to C2 over C1 times Q1. Well, C2, we called 8 microfarads. And C1, we called 4.00 microfarads. And that's times Q1. So we see that Q2 is actually going to be equal to 2 times Q1. So in this case, Q2, which is this guy, is going to get twice as much charge, even though it is the bigger capacitance. Remember, I said it behaves oppositely like as a resistor does. The biggest resistance gets the least current, but the biggest capacitor gets the most charge. And I think I might have misstated that earlier, but that's what happens. The bigger one gets the bigger one, unlike resistance where it's opposite with charge. So now I got Q1 is equal, or Q2 is equal to twice Q1. I can plug that into equation 2. I will call this equation 1 prime. So I'll say 1 prime into 2. That's going to give me 2Q1, no. I solved for Q2 so I can eliminate I solved for Q2, so I'm eliminating Q2. So this needs to be Q1 plus 2Q1 is equal to 432 microcoulombs. So that means Q1 is equal to 432 microcoulombs divided by 3. Well, that should be 120. That would be, no, that's not right. I'm going to do actual math with my calculator this time instead of trying to do it in my head. 432 divided by 3. Oh, it's 144. So Q1 is 144 microcoulombs. That's how much charge is going to get on Q1. Now I can use 1 prime, and that's going to give me that Q2 is equal to twice Q1. So that's going to be 2 times 144 microcoulombs, which equals 288 microcoulombs. So Q2 is 288 microcoulombs. So I've now gotten the initial charges. Now here's the weird part. I'm going to now take this 288 microcoulomb, which is actually corresponding to a 8.00 microfarad capacitor. And I'm going to take the positive side and connect that to the negative side. Boy, I drew a big capacitor there. I didn't really need to draw it that big, but I did. Okay, I'm going to connect that to the negative side, and I'm going to connect the positive of this one like that. So they're not connected yet, but they're going to be. And in this case, this one's going to be the 144 microcoulomb, but the 4.00 microfarad capacitor. Okay. So what you see is when I connect these, this is negative and this is positive. So what I'm going to get is Q. Let's say this is the positive side as I wrote it here. So we're going to say Q1 minus Q2. That's going to be the net charge we have left because the pluses are going to cancel out the minuses until it runs out of pluses or minuses. And then what you have will be the new charge on the capacitors. Okay. So you're going to have, in fact, the new charge on this capacitor, which is this one's capacitor 2 and this one's capacitor 1. You're then going to have Q1 here and Q2 here. Like that. So this sides are both going to be positive. So that means Q1 plus Q2 is going to be what's equal to Q1 minus Q2. So I can say Q1 minus Q2. Actually, I should have said that backwards, but anyways, I should have said Q. Yeah, it would have been nicer if I would put minus Q1 plus Q2. We'll go with that, just so it don't come out negative. It'll make things more complicated. So this side, I'm going to say 288 microfarad minus 144 microfarads equal to Q1 plus Q2. And of course, this is 144 microfarads is equal to Q1 plus Q2. So now I have one expression for Q1 and Q2. Now I need the other expression. They are in parallel, so the voltages have to be the same. So I'm going to say V1 is equal to V2. Well, that's got to be Q1 over C1 equals Q2 over C2. So now that gives me Q1 over C1 was our 4 microcoulombs. Microfarad, excuse me. And that's equal to Q2 over our 8.00 microfarads. So now I have another equation. I'm going to call this equation 3 and this equation 4. So now I can take from equation 4, I can see that Q2 is going to equal 2 times Q1 again. And now I can plug this into 3. That's going to give me, of course, 144 micro. I said farads there. That was supposed to be, dang it. Why do I keep doing that? That was supposed to be coulombs. I'm glad I caught it now, I guess. Feel free to speak up, folks. I did it there as well. If y'all see me make an error like that, I know you're learning as quickly as I'm doing it, so it's probably hard for you to keep up with every little detail. But if you see something like that, feel free to let me know. I don't get embarrassed. Everybody screws up. So 144 microcoulombs is going to be equal to Q1 plus 2Q1. So again, I'm going to have Q21. I just did the addition in my head and changed the subscript to 3 instead of 2. What a goober, man. Damn it. Still wrote it wrong. Q1. Okay. So finally, Q1 is equal to 144 microcoulombs divided by 3. 3 goes into 120 40 times. That leaves 24 left over. That's 8. So that's going to be 48.0 microcoulombs. I'll check my math. 144 divided by 3 is 48. That's good. And then, of course, Q2 is equal to 2Q1. So that means it's now going to be 96 microcoulombs. So I now have Q1 is equal to 48.0 microcoulombs. And I have Q2 after we've reconnected them, of course, is equal to 96.0 microcoulombs. So that's a kind of neat, but somewhat, conceptually difficult problem. And it's, like I said, it's just like the one your book does. I think, in fact, it's exactly like it. The only thing I changed, it looks like to me, is it looks like I use different numbers, but more or less the same process. Hopefully, between my explanation in the verbal sense and in your ability to read what it was, which was example. Let's see where that example was. That example was example 24. 24.7. So yeah, mine's like 24-7, but like I said, I did it with what I think is nicer numbers, and ultimately we still worked it out the same way. So hopefully that helps you. Any questions on that?
No, sir.
It's kind of weird, all the cool stuff you can do with capacitors, trying to work out all this junk, right? You got to conserve charge, you got to work with voltage, all sorts of cool stuff. So let's step back for a second and look at theory again. So just for a second, what I want to do is look at some of the theory behind capacitors. And for instance, you might want to say, well, Mr. Younger told me that capacitors can be used to store energy. So you might think, well, what work does it take to actually charge a capacitor? So you'd say work equals the integral of V dq. Of course, remember what we had. We had basically U equals Q times V. So you could say, if you're talking about work done on the thing, then work done on the thing is the change in potential energy. Whereas before we were working with work done by the thing, that's why we got the negative. Now we're doing work done on the thing. I could have called this Q and then multiplied by dV, or I could have called this V and multiplied it by dQ. That's what I chose to do in this case. Of course, the V for a capacitor, as we just learned painstakingly, but by numerous mistakes, is in fact Q over V, or excuse me, Q over C times dQ. So in fact, we're going to get 1 over C times the integral of Q dQ. That's 1/2 Q squared. And I'm going to integrate from 0 to big Q. So that's 1/2 Q squared. So ultimately what we can find is that the energy stored in a capacitor, U, is equal to 1/2 Q squared over C. So U is equal to 1/2 Q squared over C is one expression. And that's really handy when you know, if you want to know the potential energy and you know charge and capacitance. But what if you know charge and voltage instead? Well, then you can say, well, C equals Q over V. So Q should clearly equal CV. If I put CV in there, that's going to be C squared V squared. So one of the C's in the bottom will cancel out, and I'll get a much more familiar looking formula, 1/2 CV squared. Notice this looks exactly like kinetic energy, 1/2 mv squared. It also looks like the potential energy stored in a spring, 1/2 mv squared, or excuse me, kx squared. So that's important because the differential equations that'll come up when we deal with these circuits will be harmonic oscillator equations again, just like you learned last semester. Now, what if instead of knowing C and V, what if I knew Q and V alone? So let's say I want to get rid of the C in terms of Q. Well, the C is Q over V. So I could put Q over V squared here, and then I get 1/2 Q over V times V squared would just be 1/2 QV. So that's the three ways you can write the energy stored in a capacitor. And you can use any of them that you want, just to decide which one you know the values of, or sometimes you use it to say, okay, well, I know one of these variables are going to stay constant, so I can use the one that has that variable in it, and that'll help me. Okay. Now, here's the neat thing. If you talk about the energy stored in a parallel plate capacitor, you get a result that is highly specific for that one parallel plate capacitor, but lo and behold, it turns out to be exactly the right answer no matter what we're talking about. So I'm going to take a second and give you that. So let's do U and a capacitor. So 1/2 CD squared, I'm going to say 1/2. The capacitance we learned was epsilon 0 A over D, right? We also learned that E is equal to V over D, or more specifically, we learned V equals E times D. So I can now replace that V right there with ED. So that's the electric field times the separation squared. And when you do that, you see this D squared is going to cancel out one of those D's, and I'm going to get 1/2 epsilon 0 E squared times A times D. Now, if you think about a parallel plate capacitor, the electric field is essentially between the plates. All the stuff outside of the plates is very, very weak. So what's the volume inside the capacitor? Can you tell me that? Remember, the surface area is A, and this distance from here to here is D. Can you tell me what the volume is? The volume of that rectangle right there, rectangular space, I should say.
It would be D times the surface area.
Exactly. So what we now know is that the lowercase u, which is defined to be the total potential energy divided by the volume, is 1/2 epsilon 0 E squared. It turns out, yeah, that was a derivation that we did for a specific situation, but lo and behold, that's exactly the right answer. So electric fields, which were things in some sense we sort of made up just to make us feel better about action at a distance, all of a sudden are things that contain energy. And the energy is proportional to the square of the electric field. And that's the formula we use frequently. Okay. Your book does that, I think, in page 638 or something like that. Let me see. Yeah, 638 is where it does that. So by dividing through by that AD here, I got the energy per unit volume. So that's the energy stored in space due to an electric field being in that space. All right, any questions on that? Well, I was going to do some more. So we're not going to finish chapter 24 this week. So I'm not going to do the test this week. I'm going to, I might make it available to you Wednesday, and then it'll be due Sunday. So go ahead and keep working on your chapter 4 homework. I think you still should be able to do the chapter 4 homework by Wednesday, because all I have left is I'm going to treat dielectrics inside the capacitor, how much force it takes to push a dielectric in a capacitor, to pull a dielectric out of a capacitor, and what happens on the molecular level when you put a dielectric in there. So you can look over these last examples, example 24.8, 24.9, 24.10, and 24.11. Those are really more or less the type of problems I'm going to solve next time. And I think we're just going to have to spend 3 days on this chapter. So that's no big deal. I got to keep a mention of that. Okay. You folks are free to go. I got a lab starting up pretty soon. Let me know if you have any questions, though.
Thank you, Professor.
Thank you.
Just to confirm, no test this weekend, but do the practice test just to help with homework.
Yeah, absolutely.
Thank you.
No problem. Have a good one.
Professor?
Yes, sir.
I don't know if you had got it, but I had sent you an email on why I didn't attend class last week for lab.
Right. Yeah, I think I did. Yeah, I remember seeing Deshaun up there. It's all good. Like I said, I don't take off any kind of points or anything for missing. You're even in lab, you're allowed to miss one lab and even turn in one lab late. So it's not going to harm you. Just just remember you have that in the hole now.
Okay.
Okay. Don't worry about it. Everything's going to work out.
Okay.
Anybody else? Patrick, you have any questions? All right. Well, I'll see you folks.
No, sir, I don't.
Oh, yeah. Go ahead, Patrick.
Thank you. No, sir, I don't have any questions.
Okay. See you guys.
Thanks,
and Deshaun, I'll send you a reply on your email. I completely forgot to reply to you. I remembered seeing it, though.
Okay.
Thanks, bud. Have a good one.
No problem. Also, I also